This lesson introduced the concept of continuity of function of complex variable. So just like in the case of our real valued functions, a function f of z is continuous if it satisfies three properties. So let's give the formal definition. So a function f of z is said to be continuous at a point z equals to z naught if the following conditions are satisfied. So the first one, the value of f of z naught exists. And then number two, the value limit as z approaches z naught of f of z exists. And then limit as z approaches z naught of f of z equals to f of z naught. So that's how we define a function f of z being continuous at a point z equals to z naught. You see that the same structure or the same definition agrees with what we defined for the case of function of a real valued function. So after defining the continuity of a function of complex variable, then let's do some examples involving continuity. So continuity in terms of real and imaginary parts. So if W equals to f of z given by u of xy plus iv of xy is continuous, at z equals to z naught, then u of xy and v of xy are separately continuous functions of x and y at x naught, y naught, where z naught is given by x naught plus I y naught. for that to be very clear. But when you say f of z is continuous at z naught, then separately u and v are continuous at x naught, y naught. Conversely, if u of xy and v of xy are continuous functions, of x and y at the point x naught, y naught, then f of z is continuous at the point z equals to z naught. Now, let's illustrate this concept on a specific example. So example 1, examine the continuity of the following. So the function is f of z, piecewise defined as z cubed minus I z squared plus z minus I over z minus I, z naught equals to I, and 0 when z equals to I. So examine continuity of the following at z equals to I. So there are three things to consider. The first one is to get or to see whether the value is defined as z equals to I. Number two, determine the limit of the function as z approaches I. And then three, test whether the limit as z approaches I is equals to f at I. If that is the case, then we say that f of z equals to this definition is continuous at z equals to I. So solution. First thing, clearly, f at I equals to 0 exists. So the value of the function at z naught, which is I, actually exists from the definition. You see, when z is not equals to I, we have this function, but when z equals to I, we already have 0. So that is first condition satisfied. So condition 2, limit as z approaches I of f of z will be the same as limit as z approaches I. Now as z approaches I, we are going now to use this function in the definition, in the first formula in the function. So z cubed minus I z squared plus z minus I over z minus I. Now you see this can be written as limit as z approaches I. Z squared is common in these first two. So z minus I plus 1 into z minus I divided by z minus I. I've simply factorized the numerator. This will be given by limit as z approaches I, z squared plus 1 over z minus I over z minus I. And you see that this bracket and this one cancels out. So we have limit as z approaches I of z squared plus 1 over 1 which will be I squared plus 1, which is -1 plus 1 equals to 0. So we see that limit as z approaches I of f of z is 0. Now, since f at I is the same as limit as z approaches I of f of z equals to 0, the function f of z is continuous at z equals to I. And then that question is completed at that point. So you just have to take the three properties or three axioms to define continuity of f of z at z naught. Number 2, show that the function f of z defined by f of z equals to real part of z over z naught equals to 0, and 0 when z equals to 0 is not continuous at z equals to 0. Now, in this case, the first condition for continuity is satisfied because f at 0 is 0 as shown by the second formula. So we have to get the limit and show that the limit either doesn't exist or its value is different from 0. That will be enough to show that the function is not continuous. So here, f of z is given by real part of z over z when z is not equals to 0. Now, limit as z approaches 0 of f of z will be limit as z approaches 0, real part of z over z itself. So remember, by definition, z is given by x plus iy, and then the real part is x. So when you say z approaching 0, implies both x is approaching 0 and y is approaching 0. So this will be limit as x approaches 0, y approaches 0. Real part of z is x, and z itself is x plus iy. Now, if you remember the way we deal with limits of function of two variables, this can be obtained by first along the x-axis. So start by limit as x approaches, this can be written as x approaches 0, then limit as y approaches 0 of x over x plus iy, which will be limit as x approaches 0. As a y approaches 0, will not have this term, so we'll have x over x, which is just 1. So the value here will be 1. Again, if now we reverse the order, limit as x approaches 0, y approaches 0 of x over x plus iy, the same as limit as y approaches 0 of limit as x approaches 0, x over x plus iy, which will be limit as y approaches 0. Now, by direct substitution, where there's x equals 0, this will give us 0. So which gives us 0. Now, you see, this one shows that as z approaches 0 for two different parts, limit have two different values. And immediately we have different values for the same function. This implies limit of f of z as z approaches 0 does not exist. Now, when limit does not exist, yet existence of limit is part of the condition for continuity, then this implies f of z is not continuous at z equals to 0. So that is what we are to cover in this session. So we continue further in the next lesson.